Let m be an integer, then we define a sequence starting from m to be any function with a domain as the set of all the integers greater than or equal to m and with codomain as the set of all the reals. If f is a sequence starting from m, then we write f as f sub n enclosed within brackets and f of n as f sub n, where f sub n is the nth term of f. Now consider the sequence an where the nth term is given by 1 minus 1 over 2n. This sequence seems to converge to 1. Notice that from the second term the distance between an and 1 is less than or equal to 0.25. Also notice that from the fifth term the distance between an and 1 is less than or equal to 0.1. Since this sequence converges, we should always be able to find an n such that from that n, the distance between an and 1 is less than or equal to epsilon for every positive epsilon. This motivates us to define convergence in the following way. Let an be a sequence starting from m. Then we say that an converges to L if and only if for every positive epsilon we can find a capital N greater than or equal to m, such that for every n greater than or equal to capital N, we have that the distance between an and L is less than or equal to epsilon. We say that the limit of an equals L if and only if an converges to L. Of course, the limit of a sequence is always unique. More precisely, if a sequence an converges to both L and L prime, then L is equal to L prime. You can use the following hint to prove this. Now, does the starting index of a sequence really matter when talking about limits? We can frame this question more precisely as follows. Let an be any sequence starting from any index m. Also, let L be a real number and m prime be an integer greater than or equal to m. Then an converges to L if and only if an starting from m prime converges to L as well. The reverse direction is trivial and is left as an exercise for the viewer. We will only prove the forward direction. Let epsilon be a positive real number. Since an converges to L, we can find a capital N greater than or equal to m, such that the absolute value of an minus L is less than or equal to epsilon for all n greater than or equal to capital N. We will choose n prime to be the maximum of capital N and m prime. Then clearly n prime is greater than or equal to capital N and also greater than or equal to m prime. Thus, for all n greater than or equal to n prime, we have that the absolute value of an minus L is less than or equal to epsilon. This completes the proof. It also turns out that convergent sequences are bounded as well. You can prove it by using the following hint. Now we will take a look at some important limit laws. Let an and bn be convergent sequences, then limit of the sum is equal to the sum of the limits. Limit of the product is equal to the product of the limits. Limit of the reciprocal of bn equals the reciprocal of the limit of bn, given that the sequence bn is non-zero and converges to a non-zero limit. The first one can be proved easily by using the triangle inequality. To prove the second one, you can use the following hint. We will now prove the third one. Let epsilon be any positive real number. Since bn converges to L, we can find an n1 greater than or equal to m, such that for all n greater than or equal to n1, we have that the absolute value of bn minus L is less than or equal to epsilon times L square divided by 2. We can also find an n2 greater than or equal to m, such that for all n greater than or equal to n2, we have that the absolute value of bn minus L is less than or equal to absolute value of L over 2. If we choose capital N to be the maximum of n1 and n2, then the absolute value of bn minus L is less than or equal to epsilon times the absolute value of L square over 2, and also less than or equal to the absolute value of L over 2 for all n greater than or equal to capital N. Since the absolute value of Bn minus L is less than or equal to absolute value of L over 2, we have the following, which implies that 1 over the absolute value of Bn is less than or equal to 2 over the absolute value of L for all n greater than or equal to capital N. Thus, for all n greater than or equal to capital N, we have that the absolute value of 1 over Bn minus 1 over L is less than or equal to epsilon, which completes the proof. Now there are some more limit laws, but all of them follow from the ones mentioned before.